for the lesson. So let me, close the very thing I needed. Let's get the PowerPoint. And I'm actually going to post the PowerPoint slides in D2L for you. So if you needed to, you could go back and get the slides if nothing else. And rather than going through the actual PowerPoint, I'm just going to click through the slides because it's simpler. So we're going to start off talking about something called integration. And the best background, common sense explanation that I can give you for what integration is you've learned to drive forward. You learn how to take derivatives and use them. So you learn how to go forward. And you know that if you practice a long time, just like really driving a car, that you get pretty good at it after a while. You may not practice long enough to get really, really good at it. None of us is ever perfect at it. But you get better at it as you practice. Well, now we're going to put the car in reverse. And if you remember when you were first learning to drive, learning to back up was probably the hardest thing you ever did in your life. But as long as you can keep your mind around the fact that all we're doing is going in reverse, so we've got steering wheel still, we can still look out a window, we will be able to do it, and you can probably back your car up now fairly well as long as I don't ask you to drive 60 miles an hour backing up. So nobody ever gets, I think, as good at doing doing integration, which is what antiderivatives are, as they do in actually doing the derivatives. The derivative seems to finally click and make sense. But some of this that we're going to do in this chapter is going to finally bring what you did in chapter 11 you struggled with. It probably is going to finally bring it back into focus for you. And there's going to be something that clicks like, oh, that's why we looked at it. So be patient and don't freak out. Okay? First topic is antiderivatives themselves. This is what an antiderivative is. This is a math definition. Basically, in English, what this says is that if capital F prime is equal to some function, little f of x, then capital F of x is the antiderivative of f of x. Now, to put it another way, if you have an antiderivative, it is basically a rate of change formula. So you are given the rate of change formula for a function and asked to go back and figure out what the function was. And that sounds difficult, but you've actually done it before. You did that as you went through Chapter 13's homework when we actually showed you the graph of a derivative and said, think about when was this function increasing, when was the derivative positive, when was this function decreasing, when was the derivative negative, when was the function reaching a max or a min, when was the derivative equal to 0. So as long as you looked at a graph, you actually could kind of go backwards in your head. Okay, this is the derivative, what does that mean the graph look like? But now we're going to have an algebraic way to do it. And the good news is that before we finish tonight, we will also have a way to do these on the calculator. If we have actual numerical integrals, we can do them on the calculator. So if you have two functions, f of x and g of x, they're both slope formulas. The antiderivative is basically you've got the slope formula and you've got to go back to the functions. Then there is a constant c such that if you subtracted the two functions, the only difference between them would be that constant. Now, to make that make any kind of sense, you've got a picture on the front page of your notes. So these are three derivatives of three different functions. But they all look the same. What's the only difference between them?
Where they crosswise.
where they cross the y-axis. And what is it in a function that tells you where that function crosses the y-axis? Like if you've got ax squared plus bx plus c, what tells you where it crosses the y-axis? It will be the number at the end of the function, the c, whatever that constant is. And that's the only difference here. G of x has some constant, like maybe plus 3 or plus 5 on the end of it, whereas f of x doesn't have a constant at the end unless you consider that it's actually plus 0, because it goes to the x-axis at 0, so it doesn't look like it has a constant, but it does. That constant is 0. And that h of x has a negative constant at the end, so whatever h of x's rule is, at the end of it, it had to have a minus some number, like maybe minus 3 or minus 5. Okay? So these functions look alike, but they are actually derivatives of different functions because they all differ by a constant, and that means their parents also differ by a constant. Okay? So that's what leads us to this definition of an indefinite integral. The integral, capital F prime of x, is equal to the slope formula for capital F of x. That's what little f of x is. Then the integral of the slope formula is capital F of x, the parent of the slope formula, plus some constant. For any real number, we don't know what the constant is. We don't have any way of finding out what the constant is. And we generally don't need to. We don't have any real need to find out what the constant is. The first one is basically we're going to go in reverse on the power rule. When you're taking a derivative, the power rule says you take the power that's on the variable and you bring it down in front of the variable and multiply it, and then you reduce that power by 1. If you're going to go backwards, then you start at the end of that process and you take the power that's on what you have, and you know it had 1 subtracted from it, so you add that 1 back. And then where you dropped it down in front, now you need to take that power and put it underneath and divide to get back to the original thing that you had. The best one I can think of right off the top of my head to explain is if x raised to this power in this case was x squared, the integral of x squared would be, okay, it came from an x cubed, right? Because we know that the derivative is 1 power down from the actual function. So it came from an x cubed function, x to the 3rd power, and then we're going to take that 3rd power and drop it down underneath, so it was actually 1/3 x to the 3rd power, or x to the 3rd power over 3. And what happened when we had that original function was we took that 3rd power, reduced it by 1. We're taking the derivative, so we put that power down in front and reduced it by 1. So we're just trying to go backwards. The only thing is, this only works as long as n is not equal to -1. Because if n is equal to -1, then -1 plus 1 leaves your power on x to be 0, and then it won't work. It won't work because not only is the power 0, which is not a big deal because that makes that 1, it would make the denominator equal to 0, which is undefined. So we can't use this rule if the power on x is -1. We have to have a special rule for that one. So here's our first example. This example says find the integral of 1 over t to the 4th dt. dt says what was in front of me is a derivative. Okay, that's really what dt says. This is with respect to t. This is a derivative with respect to t. So the first thing we have to do is we have to write 1 over t to the 4th as t to the -4 power. You have to bring it up out of the denominator and make its power negative. And then you have it in the form that we can work with it because it's t raised to a power. So our first step is to Take -4 and add 1 to it. That changes the power. And then also do the same thing. Take that new power and divide by it. So then this becomes t to the -3 over -3 plus the constant of integration, c. And that's equal to -1 over 3t to the third if you want it that way. I am perfectly happy if you leave it this way, but if you want to change it to this so that you don't have the negative exponent, that's fine. My math lab should take both of them and not question either one. I wonder if we can close those any better. If I can figure out which ones it's actually coming from. Probably this one. And there's the problem. That helped a little bit. That's better. So anybody have any questions on this one? I don't want to go too fast and leave you lost. Okay, let's try another one. This one only differs in the fact that we're going to have a constant in front of whatever that expression is. And what this rule says is that if you've got a constant times some function of x, like 3x squared, that you can actually pull the constant out in front and just carry it along for the ride, kind of like we did with the derivatives to start with. You know, if you had that constant, it just stayed in there, and then the power dropped down and multiplied by it. Well, it's going to be the same thing this way. We're going to just keep it out front, and then whatever the power does, it's going to go underneath. So it's going to divide. And the other one says that if you've got an expression that's actually the sum or difference of two different expressions, a polynomial in other words, that the way you do them is kind of the way we did derivatives. You know, you differentiated x squared plus 2x. First you differentiated x squared, and then you differentiated 2x, and you put it together. That's what we're going to do here. We're going to take the integral of the first function and add or subtract it with the integral of the second function. So that makes sense, we're going to do the integral of 6x squared plus 8x minus 9. And that says dx. That's just saying whatever this is, this thing in front of me is a slope function. So by extending the sum and difference rules to more than two terms, you're going to take the integral of 6x squared plus the integral of 8x plus the integral of -9. But what's going to happen is that you're going to pull that 6 in front of the x squared out in front of the integral and just let it come along for the ride. And then you're going to pull that 8 in front of that x out in front of the integral and just going to hang it out there and keep it with you too. This one takes a little more thought. The integral of a constant is not 0. The derivative of a constant was 0. But the integral of a constant is x. Now basically the reason that that's true is because -9 could just as well be 9x to the 0 power. And it would still be just -9. And if it was x to the 0 power, if you add 1 to the power, that becomes x to the first. And you divide by x, that's x to the first over 1, and that's just x. So anytime you're doing the integral of a constant, it's going to be whatever that constant is times x. And in the last step, the only thing they did was they said, you know what, 3 goes into 6 2 times. And 2 goes into 8 4 times. So they got rid of the fractions and said it was 2x cubed plus 4x squared minus 9x plus c. Okay? Now think about this for a minute. Let me write that expression down. because I want to show you that there is good that can come from this. It actually is possible to check your answers. So here's what we've got so far. We have found the antiderivative of 6x squared plus 8x minus 9. So what we have now is the function that we started with. And if we take the derivative of the function that we started with, we get 3 times 2 is 6x squared, 4 times 2 is 8x, 1 times 9 is negative 9, and then that x disappears. Plus there was some constant out here that when we took the derivative of it, it disappeared. So there's your derivative. And the derivative is the same as what we started with. So you can go backwards, but you can also take what you get when you get there and check to make sure that you went backwards the right way. This one is a little bit trickier. You have to think about the same kind of things that you thought about when you were doing derivatives to start with. You have to think about, okay, how can I get rid of radicals? You can turn them into fractional powers. How can I bring things up out of the denominator? You can make their powers negative. So we have the integral of x to the third minus 2 over the square root of x. That's much more easily written as the integral of x cubed over the square root of x minus 2 over the square root of x. Basically, you're just putting both terms in the numerator over their own version of the denominator. And then convert that square root into a 1/2 power. And then by the rules for exponents, this converts to x to the 3 minus 1/2, and 3 minus 1/2 is 5/2. Because 3 is 6/2, and 6/2 minus 5/2, or minus 1/2 is 5/2. And then on the second part, since this is a constant and we can't do any subtraction, we can bring the x to the 1/2 up to the numerator and call it x to the negative 1/2. And now we can apply the power rule. So the power rule says, take x to the 5/2 and add 1 to 5/2. That would be x to the 7/2. And then drop that power down underneath and divide by it. Minus 2. 2 is just coming along for the ride. It doesn't do anything else. Negative 1/2 plus 1/2 plus 1 is positive 1/2. And then you divide this one by 1/2. And then you add on your constant of integration. See if I can move that where it's not quite as much in your way. And then you add, once you add the constant of integration, actually you could stop right there where I've left my cursor. You could stop without going to that final step. But if you want to go to the final step, basically remember that if you're dividing by 7/2, you're multiplying by 2 over 7. And if you're dividing by 1/2, you're multiplying by 2. So 2/7 comes up and goes in front, times x to the 7/2 minus 2 over 1 times 2 gives us 4. So if you want to clean it up a little bit, you can, but there's nothing wrong with that first version there. This is actually fine, just like it was with derivatives. It's not the simplification that's the big deal. Does anybody have any questions on that one? And that one wouldn't be nearly as easy to go backwards and find out, you know, did I for sure do this right? But you could still do it. You could still use your power rule on both of those and actually take the derivative of what you got at the end of that. And it would go back eventually with some algebraic simplification until it looked like what we started with. And you could easily go take the derivative of this and get back to that step with no problem. Any questions? Okay, there are also rules for how you do exponential functions. Basically, if you remember when we were doing derivatives, what was the derivative of e to the x? It was e to the x, right? Well, then that tells you that the integral, the antiderivative of e to the x is e to the x plus a constant. If it's e to the kx, the only thing that's going to be any different is you're going to divide by the k. And remember that k can't be 0 because it's in the denominator. And in both cases, you've got a constant of integration on the end. Now, for any number a that's positive and not 1, it has to be greater than 0 and it cannot be 1. It can be a fraction or it has to be bigger than 1. Then a raised to some power, if you do the integral, goes back to being a to the x over the natural log of a. And if you look back at your derivative rules, you'll see that it's just a reversal. And then a to the kx would simply be the same as what we did with e to the kx. It will be a to the kx over k times the natural log of a. So that last one is actually just a combination of the third one and the second one. It's saying there's nothing special about a being the base. If you've got a constant in your power, bring the constant down to the denominator and divide by it. I forgot you didn't have one.
Is that next one?
Sure. I need to give it back to y'all. And then the last of them, remember at the very first rule I said you've got a power rule and it works for all the powers except -1. You can't have -1. Remember that x to the -1 is 1 over x. And if you remember when you had the natural logarithm of x, its derivative was 1 over x. So since we're going backwards, the integral, the antiderivative and integral are the same thing. The antiderivative of 1 over x is the natural log of the absolute value of x. And that's x to the -1 taken care of. So if you've got that, it's actually very easy to take the derivative of it. Here's an example of the rules we just looked at. We've got 3 over x. Remember, this time that's not, the variable is in the numerator. Now it's in the denominator. So actually, 3 over x is the same thing as 3 times 1 over x. Okay? Pull that constant out of the numerator and get a 1 up there. So that way, when you do the antiderivative of 1 over x, that's the natural log of x. And then that 3 that you pull down in front, that 3 just multiplies. And then the derivative of e to the negative 5x, and there is a typo in this. I don't know how well you can see this anyway. E to the negative 5x would be minus 1 over 5, not 1 over 3.
Yeah, the first one says -3.
Yeah.
It's just the solution. The first one says.
Yeah, I think that's right. So I'm not sure how this changed to this. Because I think I actually, yeah, I didn't put those in there. Those are not the same. That's not the same program that I used to build mine. So this is a publisher's. Maybe I can fix it. If it'll let me open that thing. No. We're stuck. So you're taking the integral of the original. So it's bring that 3 down and divide by it, which is the same thing as multiplying by 1/3. And then the rest of it is just e to the x. And it would be perfectly okay just to say that that's e to the negative 3x over 3. I don't care if you pull the 1/3 out in front or not. That really doesn't matter. You can just divide by the 3. And don't forget to put your constant of integration on the end. Not because it's a huge, big, terrible deal as far as, you know, unless you had a reason to need to know what that constant was, but because if you don't put the C on the end of it, then my math lab's going to count it wrong. So if it says that's not right, look carefully and make sure you entered your C at the end of the integral. And believe it or not, folks, that's all there is in the first section. That's really it. Now I'm going to go on to the second section, but then we're going to take a break. Because I know everybody really struggled in the beginning with chain rule. And yes, you have to undo chain rules. So before I go into 15.2, I'm going to remind you of how you have to do a chain rule problem. I'm actually going to go pick one of the functions out of here. Okay. This is the expression that we've got that we wanted to integrate. What this tells us is that originally we had some inside function that we had taken the derivative of. And we also had an outside function that had a power on it that we took the derivative of. The reason that we have to be careful about this is called a substitution, is whatever the derivative of inside the parentheses is, it has to be outside the parentheses for us to undo the chain rule. So the derivative of whatever's inside has to be present outside the parentheses. The derivative of 4x squared is 8x, and the derivative of 8 is a constant, 0. That's the constant rule. So 8x dy dx, we actually just keep the dx portion of it. We call it 8x dx because 8x is the dy. So just to try to further illuminate, if you've got something to the fifth power and you're taking a derivative of it, what you do is you bring the 5 down in front of the power and reduced it by 4. And then whatever was inside here, you took its derivative. Say this was x to the third plus 2x. You took its derivative and you multiplied by it. So when you try to undo that, you've got to have this derivative present before you can undo it. And fortunately, in the problem that we're looking at, we do. Now, when it talks about u, think of u as just being whatever's in the parentheses. Okay? In this case, u is 4x squared plus 8x. The derivative of u is 8x dx. Since 8x dx is already present in the problem, then really all we're doing is we're taking the derivative of something to the 6th power. The 8x dx just goes away. It's like it's not even there. It really is just part of the dx part of the problem. So we're really just taking the antiderivative of something to the 6th power, which is that same something to the 7th power divided by 7. So since we've got parentheses with a 7 on the outside of it, 4x squared plus 8 is what goes inside those parentheses. And then we divide by the 7. So when we did it as a derivative, we called it chain rule. When we do this in antiderivatives, we call it substitution. But I think they really should have called it the unchained rule, because you're trying to unchain it and get it back to what it was. So I'll give you a minute to write those down and think about, do you understand how we did what we did? Any problems? We good? I know it's hard to get your mind to go in reverse. That's why I don't want to go too fast with this. Which is also why we're not going to cover chapter 16. I don't want to rush it. Okay, let's try another one. Find the integral of x to the third times the square root of 3x to the fourth plus 10. Here again, we want to change that square root eventually into something to the 1/2 power because it'll be easier. But in the beginning, what happens is what's under the square root is going to be our u. It's going to be the inside function, what we call the inside function in the chain rule. And the inside function is 3x to the fourth plus 10. And the derivative of 3x to the fourth plus 10 is 12x to the third dx. Well, I got an x to the third. I don't have a 12. What I can do about that, though, is that I can put a 12 inside the integral so that I have 12x to the third. And then I can get rid of it by also multiplying the very front of the integral by 1 over 12. Because 1 over 12 times 12 cancels each other out. So basically you're putting it in and then taking it back out. And once you've got that, you've got your du. So basically you're going to take this expression and say that this is actually 3x to the fourth plus 10 in parentheses to the 1/2 power, which means that you're going to bring that 1/2 power up to 3/2 by adding 1 to it, and then you're going to divide by 3/2, and that 1/12 just keeps trucking along, right along with the problem. And actually at this point, even though it doesn't look like it ought to be. At this point, you could actually quit, and it wouldn't hurt anything. Because that's the equivalent to the rest of the expressions that are here. What they've done to get from this step to this one is they have taken the fact that if you divide by 3/2, then you're going to multiply by 2/3. So they took 3/2 and multiplied times u to the 3/2 and put the 2 up there with the u and put the 3 in the denominator. And then they further multiplied and cancel by saying 2 goes into 12 6 times, and 6 times 3 is 18. So all the way cleaned up, it's 1 over 18 times what was in the parentheses to the 3/2 power plus c. Now, if you can do one like that, you've got it beat. That's probably the hardest one. Does anybody have any questions? Anything you can't figure out? Make sure you know where everything's coming from.
Where did 1 over 12 come
Because I put a 12 inside the integral so that I would have my derivative of the inside. So in order to get rid of the 12 that I arbitrarily just tossed in there, I multiplied by 1 over 12 on the outside.
from? I wouldn't see
That-
that.
Yeah. And it's not showing up as well because there's so much light, but these are both actually blue to show that I put them in at the same time. Any other questions? If you don't know where something came from, say so. Because we need to make sure you understand what you're doing. Nobody's going to think you're done, believe me. This is not easy stuff.
What part did you say we could stop at?
You could actually stop, if you go ahead and put 3x to the 4th plus 10 right there, where I've got my cursor, you could actually stop there. And it would be all right. They just went ahead and did a bunch of arithmetic cleanup before they actually plugged the function back in at the very end. So you could have given it 1 over 12 times, in parentheses, 3x to the 4th plus 10 to the 3/2 power, over 3/2, and there's really nothing wrong with that. It's the same expression. You ready to try another one? Okay, here we've got what appears to be a quotient rule, and I can hear people already going, oh, please don't tell me there's a quotient rule antiderivative. No, there's not. There's no product and quotient rule. We're going to treat this as if it is a chain rule still. We're basically going to separate this out. This is the most complicated expression in the mixture of expressions. Whatever is to the highest power is going to wind up being your inside most of the time. So if I choose this to be my substitution, my inside function, then its derivative is 2 times x is 2x, and the derivative of 6x is 6 dx, which is the same thing as 2 times x plus 3. And it's kind of necessary that you actually see that this and this are the same thing, because then you'll realize that you do have part of that derivative up there. You have the x plus 3. Okay? You do have that. But you don't have the 2. So what you do to be able to put the 2 in is you plunk that 2 down in the numerator of that problem, But then you go out in the front of the integral and you multiply by 1/2 to take it back out. You need that 2 inside to be able to do the antiderivative. But you also need the 1/2 to cancel it out in the end. So now that I've got the derivative, what I have is the derivative of 1 over u. That's not really very well spelled out right there. That's 1/2 times the derivative of this over it. And if I move this du out here to the side, then that's really 1 over u. It's really 1 over x squared plus 6x. And remember, I can't just move that up to the numerator and give it a -1 power because this doesn't work for -1 powers. So what I do is, since I've got 1 over something, is I take its natural logarithm. Because the derivative of natural logarithm is 1 over something. So the antiderivative of 1 over something is take the natural log of it. The 1/2 all the way through is just riding along. I threw it in, I've got to keep it. So once I realize I'm just taking the natural log and adding a constant, then it's the natural log of that expression, x squared plus 6x. And you really do need to come actually all the way to this part of the problem. You can't stop at any of the points in between. You actually have to get your function back in there. You've got, if you start typing in things with u's, in my math lab, it's going to say, what?
Where's the 1/2 coming from? I don't understand how that's getting out there. I don't know.
Okay, do you understand why I need the 2?
Yes.
Okay, so I put the 2 in here. But now I've changed the value of what's in the antiderivative by a factor of 2. I need to get rid of that factor of 2. What's 1/2 times 2? 1. So that means it canceled out. It doesn't change anything. So that's where it's coming from. Whatever the constant is that you have to put inside, whatever your multiplier is, you take 1 over that same number and put it out in front of the integral. So that you can have it where you need it and yet not have changed the value of the problem. Does that make sense? So basically, I'm giving you the rule at the end after I show you how to do the examples because I think it probably is easier to summarize this way. If you have the function raised to a power, some function inside brackets or parentheses raised to a power, as long as the derivative of that function is present in that integral, then you simply use the power rule. If that derivative is not present and you have to insert a constant, then you insert that constant, you insert that multiplier, and just put 1 over that multiplier down in front of it. It will be the same thing if you got the derivative over the top of the function itself. If the function is in the denominator, that's going to be 1 over x, as long as the derivative is out there somewhere. So 1 over whatever that function is means that as long as I've got that function's derivative out there, again, I have to maybe add a constant or whatever I need, then it's going to be the derivative of this function is going to be the natural logarithm of that function plus a constant. And you could have e raised to some power. And e raised to some power is actually just like it's its own derivative. It's also its own integral, its own antiderivative. But if that power is a function, then you still have to have the derivative of that function in the antiderivative before you can proceed. But as long as you've got it, then you just shove it over to the side and say, okay, you're doing your job and I don't need you. I need to focus on how to undo what's been done. Okay? So, and I like this summary a lot better actually. It says, in general, when you need to do this substitution method, this unchain rule method, basically what happens is that there's only going to be 3 cases where you need to do it. One of them is going to be that there's a quantity under a square root, a cube root, or raised to a power. And a root and a power are actually the same thing, it's just the root is a fractional power. Or you're going to have the quantity is in the denominator, or you're going to have it as the exponent on an e. Now, actually, I think you probably could have it as an exponent on a base other than e, but in logical use, we rarely have that happen. Most of the time, our base is e. And this actually is just to tease you. I left it in there. I don't think anybody in here has a TI-92 or a Voyager. There are calculators out there that will actually calculate integrals for you in algebraic form and tell you what the answer is. And just to put you on a level playing field with my other class, because they're all technology geeks, they do also have things like, let's see, I think Symbol Lab, I think. There are you can Google almost anything, and you can Google how to find an integral. There are programs that will let you double check your work and make sure that you did it right. Now, we will have a use for the calculator, but unfortunately we can't use it here because we don't know what the constant is. We don't have any, we're working with indefinite integrals. So the calculator isn't going to be of much help to us in sections 1 and 2. It'll be a lot of help to us in section 3, 4, and 5, because there is a way to do a lot of this work when we get into the numerical end of it on the calculator with a built-in function. Just like it would take derivatives, inderiv, it will also do integrals. So at this point, it is 7 o'clock, and I think we need to take a break. Okay, section 15.3. This gets into the applications. Why do we want to do integrals? What good are integrals? And as we get into the area of the definite integral, I can show you business applications where they're useful. But we're going to start out with one that hopefully we can all kind of understand what's going on here. This is a quarter of a circle. Okay? And we could find the area of that full circle and divide it by 4 because we know what its diameter is. Its diameter is twice 2 because its radius is 2. So with that information, with the radius or diameter, either one, we could use the A equals pi r squared and be able to figure out what its actual area is. Okay? And then we would divide that area by 4 and have the area here. And in fact, it should turn out to be pi because pi times 2 squared is 4 pi, and we've got 1/4 of the circle, so the answer should come out to be pi. So what we're going to do is look at, is integration going to tell us the right answer? And we're going to see that it will. So you don't really need to take much in the way of notes on this because I pretty much laid all these out on your notes. If you wanted to approximate the region, if we didn't know a formula to find the area of the figure, if you wanted to approximate it, we could try to put 2 rectangles in there because the formula for finding the area of a rectangle is really easy. It's the length times the width. Or if you wanted to think of it that way, it's the base times the height. It's the same thing. If we divided this area up, we put one 1-unit wide rectangle with its left side aligned with where the top of the circle is, and then another 1-unit wide rectangle with its left side aligned to where the top of the circle is, and we found the area of this rectangle and this rectangle, it would overestimate the area of the circle. And actually, if you look at this part that's hanging outside, it overestimates by quite a bit. If we use just one rectangle and put it inside, well, it underestimates the area by a whole lot. But if we did those two different estimations, and we added them together and divided by 2, if we averaged them, it would, some of the underestimation would count out some of the overestimation, right? So that might help a little bit. So actually, if you look at this approximation, this is quite a bit more than pi. This is quite a bit, quite a bit less than pi. But if I added this number and that number, I would get a lot closer to pi than what either one of them are, if I just average those two. But I'm still not going to get a really accurate approximation. So what I want to do, actually, is think, well, okay, what if I moved the rectangles a little bit? What if I moved them so that the midpoint of the rectangle would actually give me a little less error, because here that's underestimation and there's a little bit of overestimation, so they kind of cancel each other out a little bit better. And then here's some underestimation, but some of this overestimation cancels that out, so there's a little bit less error. And I actually went ahead and did the math on both of those, and it actually turned out to be 3.259, which is a little closer to pi, but it's still a little bit too big. We could improve the accuracy, regardless of which kind of rectangles we used, if we would simply use more rectangles. Because it turns out the area here is closer, but still not pi. But if we use more rectangles, it gets closer. And if you keep on adding more and more rectangles, eventually what you come down to is the idea of what is a definite integral. Back in chapter 11, we talked about finding limits, and we let h approach 0. What we're doing now is we're letting h approach 0. We're using more and more rectangles, which means each rectangle is going to be skinnier. It's going to start out wide, but it's going to get skinnier and skinnier and skinnier and skinnier and skinnier, until finally they're so skinny they look almost like a line. But when they get to that point, it's going to just almost perfectly fill in that curve. And that's what this definite integral is saying that you're going to do. So in English, what that says, because I know that's hard to read, in English, if we let the number of rectangles increase, that is, approach infinity, as that happens, the sum of the area of the rectangles will grow closer and closer and closer to the actual area beneath the curve, between the curve and the x-axis. This is where the calculator comes in. With the calculator, you can actually use the calculator's built-in function and calculate a numerical interval. And that's what we're going to do for this first example. If you have the newer TI-84, yours is going to look just like this. If you don't have the newer one, it's not going to look exactly like that. It's going to look more like this down here. On the TI-83 or the TI-84, either one, you press the math button. And the calculator's broken. Okay, now it's fixed. So you press the math button, and on the 84 it may not be in exactly the same place, but if you used nderiv on your 84, it's going to be the next command after nderiv, and it says function integral. Now, when you hit function integral on the 84, it may bring up a window that looks like this. And if it does, just fill in the numbers. What we're doing is we're integrating from 0 to 2, beginning at the y-axis and going over to 2 to get all that quarter circle. And the equation of that circle is the square root of 4 minus x squared. So the way that you enter it in, and on the 84 is just fill in the boxes. On the 83, you have to put the expression, which is the square root of 4 minus x squared, then a comma, then x, what you're integrating with respect to, what is the independent variable, and then the bottom limit and then the top limit. It always goes A to B. If you put them in backwards, it'll tell you the area is negative. So be careful that you put them in from the bottom one and then the top one. So, second square root x squared minus, oh wait, whoa. Getting ahead of myself. Or minus the square root of x squared. Close the parentheses because it opened them up for you. Put a comma. We're integrating with respect to x. And our definite integral for this is going to be from 0 at the origin to 2 where the first x-intercept is. And hit enter. And it takes it a few seconds because it has to do this numerically. And it comes back and gives you the same thing that you would get if you ask it for the value of pi. Pretty close. And that's because numerical integration is not perfect. But if we were going to round that to, I don't know, about 6 decimal places, I'd say that's pretty good. Close enough. Right? So you can do these numerically. Now, to understand why this works, we're going to try to approximate, oh great, now it's really bright. We're going to try to approximate the area of a straight line. This is the line f of x equals 2x. Now we could actually find the actual area there really easily. It's 1/2 the base times the height, and the base of that triangle is 4, and the height of that triangle is 8, so 1/2 times 4 times 8 would give us the exact answer. But this approximation is actually going to work very well because all of the overestimations exactly cancel out all of the underestimations. So if you add up, basically what this is saying is that the first interval begins at 1, and the value of the function at 1, I'm sorry, it begins at 1/2, because we're using midpoint rectangles. So the value of the function at 1/2 is 1. It goes up to 1. So this rectangle is 1 unit tall. The second rectangle is 3 units tall. The third rectangle is 5 units tall. The fourth rectangle is 7 units tall. And all of them are 1/2 unit wide. So 1/2 times 1/2 times the total of all these gives us the exact same area. The area that we're supposed to get.
Why would the width be 1/2?
I'm sorry, it's 1. I said 1/2. Thank you. Thank you. It's 1 because we're using 4 rectangles going from 0 to 4. So actually, if you take the area of this first rectangle, it's 1 times 1. The area of this one is 1 times 3. The area of this one is 1 times 5. The area of this one is 1 times 7. Right? So I could just add all these numbers up. 1 plus 3 is 4, plus 5 is 9, plus 7 is 16. And what is 1/2 times 4 times 8? 16. Okay? So this is the idea of what integration is doing on things that we can actually get the real answer for. So this is an explanation of what we just concluded. Using the formula for the area of the triangle is 16, and that's the exact value of the area, but the approximation equals the exact area because our use of the midpoints in each of those subintervals distributed the area evenly above and below the actual line. So they cancel each other out. This is some fancy calculus language for exactly what we just got done doing. Okay?
So if
I will show you how to do them. I mean, the arithmetic on doing them by hand is simple because you're just finding areas of rectangles. And I'll show you how to do the calculator to actually make those calculations go faster if you do have to go by hand. So this problem says it's a problem about oil leakage. So this is where things do become important. The next figure that I'm going to show you shows the rate that oil is leaking from a machine in a large factory in cubic centimeters per hour with specific rates over a 12-hour period given in the table. And we're going to approximate the total amount of the leakage over a 12-hour shift. So the graph that we're looking at here is actually the rate of change in the leakage. So the leakage is actually increasing for the first 2 hours of the shift and starts to decrease, and it decreases until somewhere around 5 hours of the shift. Between 4 and 5 hours it bottoms out, and then it starts increasing again until it gets to 8 hours, and then it starts to decrease again until it gets to about 10 hours, about 10 or 11 hours, and then it increases and then it decreases again. What we've done is we've divided that 12-hour period up into 12 rectangles. Now, we don't have the formula for this function, so we're not actually doing a calculus integration at this point. We're actually just doing something geometric. So these 12 rectangles, according to what's in this chart, at the beginning of the first hour, we're using left rectangles here. At the beginning of the first hour, the leakage was 15.2. At the beginning of the second hour, which is at x equals 1, the leakage rate was 18 cc's per hour. By the time we get to the beginning of the third hour, which is at time t equals 2, then it's up to 18.8. At 3, it's 14.1. At 4, it's 9.5. At 5, it's 9.6. So we're basically reading these off of the graph, but we're being given more accurate results than what we could probably get on our own. So now we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 rectangle heights, and each one of those rectangles is 1 unit wide. So actually, the first rectangle has an area of 15.2, the second one has an area of 18, the third one has an area of 18.8, and so forth. So if you want to know the total amount leaked in cc's per hour, then all you have to do is add all these up. So this is going to be 15.2 plus 18 plus 18.8 plus 14.1 plus 9.5 plus 9.6 plus 13.1 plus 17.3 plus 20 plus 19.2 plus 16.6 plus 16.4. And since we do have some underestimation and a little bit of overestimation, we're taking into account that this is approximately. So the total amount leaked is approximately 187.8 cc's over that whole entire time. About 187.8 cubic centimeters of oil leak. Now, is that a lot of oil? Yeah, if it's a machine, that's a lot. So you might want to do something about it. Your maintenance men need to get their butts in there and fix that. And that's really all there is. That's the only example that I actually put up there for that section, because really that's all there is in that part of the chapter, is finding the areas of rectangles and adding them up. Now the next section actually goes right along with it. And we'll do one problem out of the next section, and then I'm going to stop and let you all ask questions about 13. Because the next section actually builds on this. And it talks about something called the fundamental theorem of calculus. And we learn to evaluate definite integrals, not indefinite integrals, but definite integrals. So we're only going to work example 1, and then we'll come back and work it again later. But basically, just to remind you of the calculator steps on this. The calculator steps on solving this problem to find this definite integral would be to hit your math button, go down and find your function integral. Your function itself is 3x squared. Your independent variable is x. And our limits of integration are from 1 to 3. And we get the answer 26. That's exactly the same thing as taking the integral of 3x squared. And the integral of 3x squared would be 3 times x to the third over 3, so it comes out to just be x to the third. And so we're going to take the formula and plug in 3 and say it's 3 to the third power, and then x to the third, if x is 1 to the third power. 3 to the third is 27, and 1 to the third is 1, so the answer is 26. So doing the integration really isn't hard, but you can always use the calculator to get the numerical equivalent and make sure that you knew how to do it and do it correctly. And actually, if you're doing indefinite integrals and you wanted to make sure that you were doing those correctly, you could actually put in a couple of limits on it and ask it to find the indefinite integral, and then look at rectangle areas. You know, put in fairly small, like maybe 4 rectangles or something like that. But that's where we're headed, and we're actually over halfway through the chapter since I did this one problem. So at this point, we are going to...
Can I ask you something before you
Sure.
start on that? The 1 to the third down here, are you getting that from over here?
Yes.
This 1 on the bottom and the 3 on the top?
These two, the way that this reads is this is the integral from 1 to 3. So it's saying this is the area between this curve and the x-axis from 1 to 3. And then when you actually get what the integral is, which is x to the third, then you put this line over here, you straighten it out, and it's still from 1 to 3. But when you do it, you always start with the bigger number and subtract the smaller number. Otherwise, you're going to wind up with negative area. Okay? Anybody else have any questions before we go to the review for the test? Okay, we will exit out of that. And I don't think I made any changes, but just in case. Do you all have any specific homework questions that you are stuck on, or any specific quiz questions that you are stuck on? Or do you want to just log in and look at your homework and quizzes for the remaining time? I'll stay here as long as anybody wants to. But at this point, if you don't...
I'm going to stay and look at my homework for at least 2 minutes.
Okay. But, if, I'll stay as long as anybody wants to, but as far as actually new material, we don't have any at this point. So we're just going to review. And I can either look at your specific problem, because I can go in my grade book and pull your work up, or I can go to the same problem you're on and work an example for you.
And the test question's going to be basically set up like the math is.
Yes. In fact, if you go into quizzes and tests, I will tell you right now that the test that is not yet listed on here, because its due date hasn't come up yet, that comes directly from this review and this review and that review. Okay?
It's gonna be online like that?
And it's online. Basically, I'll tell you how I made the test. I basically pulled up a list up of all the questions in the Chapter 12 quiz, Chapter 13 quiz, Chapter 14 quiz, and then I pulled all of those into one single document, and then I grouped them together by type. You know, there's no point in having you do 6 Tower Rule problems. So I would say, you know, from these 6, give them one of those. Okay? And I can probably tell you how long the test is, maybe. Go back
And
to,
after a test, we leave Thursday? Is that all that's-
yeah, you can take off on Thursday. Well,
Like we
don't
did.
take off immediately. Actually, what I'll probably do is at the beginning of the class, I will go ahead and do the evaluation, even though doing it before a test, I know is probably not a great time for you to be telling me what you think, because you're all on edge. But I'll go ahead and do that, and let you get the evaluation out of the way. And then, actually, my intent, since I know you guys come in here, most of you come straight from work, and you're lucky if you stop and get fast food on the way. Does everybody in here like pizza? I'll bring a couple of pizzas next time, and if you get really stressed out during the test, instead of having chocolate drugs, I'll still have the chocolate. But I'll bring a couple of pizzas, and if you feel like you need to take a break from the test for a few minutes, you can come up and grab a slice of pizza.
Do you want to
Just-
help out?
No, just bring a drink. Just bring a drink. Okay? So after the evaluation, you take the test, eat pizza, and when you're done, you go home. Okay.
On my math, on my math, I have the pre-test and the post-test, for like chapter 13. Will it help me any if you did them? No.
No, because I didn't put most of the stuff that's on those pre and post tests in the quiz. We only did what? I think maybe 10 problems in all of chapter 3 total. So,
Okay.
So we have 4 classes after tonight, and one of those is our final, correct?
yes.
So we will have our test next Thursday. Thursday after that, we'll finish chapter 15.
And then the
we'll have
Thursday
tests.
after that, test over chapter 15. And anybody that wants to can hang out after that test, and we'll review for the final if you want to. Sound good?
Sounds great.
Okay, one last question before everybody packs up and leaves. Does anybody have any preferences on what they want on their pizza?
Cheese, on me, put brownie, whatever.
Okay, a cheese pizza. Does anybody like everything? Okay, so a supreme. And maybe one pepperoni.
It's like I tell my kids, if you don't like it, pick it up.
Well, that's what I usually tell people in my family. You don't like it, hey, it was my choice and I got everything. Okay, everybody that wants to hang out, and those of you that need to go home, go forth with my blessing. It's blowy out there, so be careful.
I had one question. 14.2 will not even open up because I'm not done with 14.1. And it says I have to have 100% on 14.1 to move on.
Okay, let me see what I can do about that. That's weird.
Well, I want to get 100 on it. I don't know that.
You don't know
everybody
that you're going to be
else
able to do it right now. Let me go and look at 14.2 homework. I may have accidentally clicked something when I reset dates.
Okay.
Yes, we do not want that. What it was supposed to be giving you as a prerequisite was that you had to have done the media assignment. That's what's happened, is that that's gotten changed. That should fix that problem.
Now, you had posted like 4 integrity videos, right?
Some of those are redundant because they're the class that I have Tuesday and Thursday.
Right.
And just in case I say something in there that I might not have said to this class, I'll post theirs up there with yours.
Okay. I'm
And
just
they
going
get yours.
I'm just going through and watching all the takings and
Okay.
going through each pro. So I can do that at home.
Okay, that's fine.
Uh,
I have no issues with that.
just need help.
Can you come here, please?
Sure. Let me pause this thing so that it doesn't just continue to run. And then if need be, I'll just edit out the last part of it if we don't do any